Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss programmable logic controller interface methods. Our objective is to examine placement of emergency stop devices, auxiliary contacts, and overload elements inside variations of PLC-controlled systems, as well as discuss solutions to scenarios involving PLCs and field input and output devices operating at different levels of pilot voltage. This lecture is predicated on the assumption the viewer has watched the Introduction to PLCs lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Additionally, this lecture assumes the viewer has some general familiarity with 2- and 3-wire motor starter circuits as implemented using traditional hardwire relay-based ladder logic. For those necessitating review on this topic, you are encouraged to revisit the 2- and 3-wire control circuits lecture, available at the Big Bad Tech channel. A disclaimer before we begin. This lecture cannot, will not, and never makes the claim to replace due diligence on your part researching the specific interface mechanisms for your particular PLC or system of interest. Manufacturers offer numerous different, often incompatible interface methodologies, and the content herein can at most be considered general guidance in preparation to some specific application. Always consult the datasheet of interest for a particular system. You will recall that the fundamental operational principle of ladder logic is the establishment of two different levels of power: pilot and primary. Pilot or control signals are ordinarily low current, low voltage, low power signals that solely coordinate the action of interface elements like contactors and solenoid operated valves. Primary signals, in contrast, are high current, high voltage electrical or high flow, high pressure hydraulic or pneumatic input that does the actual work. When an interface element like a contactor or a solenoid operated valve is commanded to do so by a pilot signal, these interface components make or break connection to primary input. The separation and isolation of pilot and primary signals offer a degree of ease and safety for operators and technicians assigned to install, maintain, troubleshoot, upgrade, and repair electrically controlled systems. This concept should not be new to you, and if it is, I'm sending you all the way back to the beginning of the Electrically Controlled Systems playlist to begin anew. Look me up in 2 to 3 months when you get this concept down. Although this separation between pilot and primary signals should be simple in concept, complications to this methodology exist when we introduce a radically different means of control in the form of a programmable logic controller, or PLC. PLCs are industrial computers that, in summary, examine inputs, run a program, and issue outputs. PLCs, barring some peculiarities, closely mimic the behavior of those systems employing hardwired relay-based ladder logic. However, they are flexible, reprogrammable devices that make quick modification of a system possible without the time-consuming necessity of physically rewiring it. Two important complications exist when PLCs are introduced into the mix. 1. Does the PLC operate at the same level of pilot voltage as the interface elements like contactors and solenoid-operated valves? And 2. Can you trust a computer? Let's deal with the second issue I raised first, since it's of primary importance. I ask again, can you trust a computer, especially in an emergency? The answer is no. No, no, no. Not now, not ever. Never, ever trust a computer. When you surrender authority to a soulless and easily manipulated inanimate object, things can and will go wrong. The point being that pilot commands intended to initiate immediate specific action in emergency conditions should never originate from a PLC, but rather be physically hardwired into a system such that they can and will override a PLC. If there is one thing I learned from watching The Terminator, it is to never underestimate the duplicity and cunningness of an amoral program. This warning having been issued, a complicated system may necessitate involvement of the PLC to initiate an orderly shutdown. However, when it comes to those situations that count, never let a machine do your dirty work. When you need to kill it, and kill it dead, nothing beats a well-placed e-stop. For this reason, you'll often see PLC-controlled systems featuring e-stops wired in the following fashion. Consider a generic 4-input, 4-output PLC that operates on 120 volts AC. Let's first examine the PLC power input. A circuit breaker between the 120 volt AC source line connection and the PLC is for protection purposes and serves to completely depower the PLC-controlled system. Since this exercise has the potential to get confusing rather quickly, note I'm illustrating the line connection of the 120 volt AC source using a nauseating shade of purple, my second least favorite color, and the neutral connection of the 120 volt AC source using brown. Next, let's examine the input. Note the maintained contact normally closed E-stop is not a direct input to the PLC, but rather it serves as a hardwired bottleneck through which two field input devices immediately downstream of it must negotiate to issue input to the PLC. When the maintained contact normally closed E-stop is in the deactivated closed condition, the closure of any field input device will issue a logical 1 to the PLC. If, however, the E-stop is in the activated open condition, the closure of any field input device will not issue a logical 1 to the PLC despite repeated attempts to do so. Wired in this fashion, the hardwired E-stop directly above stream of all field input devices has effectively severed all incoming communication with the outside world without the necessity of resorting to any program to do so. Note as implemented, opening the E-stop would still keep the PLC powered up. The E-stop can also be configured as a direct input to the PLC by using another set of mechanically interlocked normally closed terminals. In this scenario, the top set of normally closed terminals still serves to sever communication with all those field input devices immediately below stream of it, and the bottom set of normally closed terminals acts as a direct field input to input 4. Used in this fashion, the E-stop still disables the field input devices, only this time the additional set of mechanically interlocked terminals allows the loss of voltage on input 4 to be used by the PLC program to initiate a specific program-based shutdown. It is for this reason the E-stop normally does not depower the PLC, but rather keeps it going to initiate the shutdown if desired. Let's now examine the output. Again, note the maintained contact normally closed E-stop serves as a hardwired bottleneck through which all field output devices also immediately downstream of it must negotiate to be energized. When the maintained contact normally closed E-stop is in the deactivated closed condition, the PLC can energize any field output device by closing the appropriate electromechanical relay. If, however, the E-stop is in the activated open condition, the PLC cannot energize any field output device despite repeated attempts to do so. Wired in this fashion, again, the hardwired E-stop directly above stream of all field output devices has effectively severed all outgoing communication from the PLC without the necessity of resorting to any program to do so. If the application warranted its inclusion, selective outputs can also maintain connection to the PLC regardless of the actuation state of the E-stop, perhaps to initiate the orderly shutdown of the system in an emergency or signal its occurrence. For example, the pilot lamp on the Q4 output is not disconnected from the 120 volt AC line connection via the E-stop. A very simple application of this selectively enabled or disabled outputs could be to light the fourth pilot lamp in the event someone triggers the E-stop. The inclusion of this single line in the PLC program would serve this purpose. A break instruction examining input 4 energizes and de-energizes output Q4. When the E-stop is in the deactivated closed condition, input 4 experiences a logical 1, and the break instruction examining input I4 does not permit logical continuity onto output Q4. Output Q4 is not energized, and the fourth pilot lamp is dark. Given this condition, the PLC is at liberty to direct the operation of this system with the rest of the program. If, however, the E-stop is in the activated open condition, most of the field input and output devices are disabled, input 4 and output 4 being the notable exceptions. In this condition, input I4 would experience a logical 0, and the break instruction examining input I4 does permit logical continuity onto output Q4. Output Q4 is energized, and the fourth pilot lamp turns on. When the E-stop is wired in this fashion, most of the inputs and outputs are still overridden. However, the selectively enabled input and outputs still allow the PLC to alert that an emergency stop condition has occurred. Various degrees of this technique could be used to initiate an orderly shutdown of a more complicated system. It should be stated that the placement of the E-stop is system and application specific and must take into account the needs of the process and those conditions that operators must be protected against. In summary, a properly placed E-stop should disable a system as quickly and reliably as possible with minimal, if any, reliance upon the PLC. In the interest of keeping things simple, let's just assume for this and the remaining applications that the E-stop is a hardwired bottleneck that disables all incoming and outgoing communications to and from the PLC. Before moving on with the rest of the contents of this lecture, Let me make a brief comment how interconnection with a PLC is represented schematically. Yes, I know I just walked you through a step-by-step tour of this system, holding your hand every step of the way using easily identifiable colors. However, if someone threw this diagram on your desk, using only indistinguishable black and white, could you honestly interpret it with any sense of grace? I mean, look at this confusing nest of wires. I've seen more sense written on the side of a bottle of Dr. Bonner's Castile soap. Given time, you might be able to interpret this, but could your lab partner? No, they couldn't. They still have trouble differentiating between left and right. It is for this reason PLC interconnections are often illustrated using a dumbed-down form of ladder logic diagrams. Recall systems using traditional hardwire relay-based ladder logic simultaneously represent both interconnection and function using techniques as discussed in the ladder logic documentation lecture. However, since a PLC's principal advantage is its reprogrammable nature, one really only needs to schematically represent the hardwired connections. Very often, a PLC-controlled system represents this schematically as field inputs simply disappearing into the PLC and outputs selectively energizing or de-energizing the field outputs. However, gives no indication as to what opens or closes these outputs. Consider our present configuration illustrated far more efficiently in the following fashion. Here, the hardwired connection between the e-stop and the two downstream field input devices, the normally closed momentary contact red push button and the normally open momentary contact green push button, is made pretty explicit. However, the field signals kind of disappear down the rabbit hole of the appropriate PLC inputs. This is to imply an isolation between the field inputs and the PLC exists, and the PLC program assumes responsibility for all incoming transmissions from this point on. Additionally, the outputs can be more efficiently represented as the hardwired connection between the normally closed e-stop and the contacts of electromechanical relays Q1 through Q3, selectively energizing or de-energizing the loads attached to Q1 through 3. However, it remains unsaid what actually opens or closes the Q1 through 3 contacts. This is again meant to imply that the PLC program is in charge of opening and closing these contacts. All a technician needs to do is to wire the devices as indicated, and it's the program's responsibility from this point forward. Illustrated in this fashion, one can think of the schematic as only partially indicating functionality, but more to the point, how the system needs to be wired such that the PLC program can direct its operation. You might see subtle variations of this illustration method employed by different manufacturers. You'll note the power connections to the PLC are not expressly illustrated using this technique. Before moving on to the rest of the contents of this lecture, I recommend pausing it and comparing the two diagrams until you understand the direct one-to-one correspondence between the confusing pictorial and the far more compact schematic representation. For the purposes of this introductory lecture, I'm going to try and use both diagrams and take my time. However, expect me to eventually abandon the hand-holding and push you out of the nest to plummet to your death or soar among your equals. Moving on. Let's now examine the placement of auxiliary contacts and overload devices in PLC-controlled motor starters. PLCs, among their many virtues, often include the ability to make use of virtual relays and their associated instructions, software-generated output instructions, and set and reset functions to create holding circuits that maintain or remember the last asserted state using purely virtual feedback. The Virtual Relays and Holding Circuits for PLCs lecture, available at the Big Bad Tech channel, discusses this topic in great detail. These techniques, while extremely handy, may not be applicable for all applications due to safety concerns. The classic exception to purely virtual feedback being a motor starter, which has the very real possibility of overloading and damaging the motor if real-world feedback is neglected. Consider a generic 4-input, 1-output PLC wired in the following fashion. A maintained contact normally closed e-stop serves to disable all incoming and outgoing communication to and from the PLC for reasons we explained earlier. Input 1 is a normally closed momentary contact red push button, and input 2 is a normally open momentary contact green push button. Output 1 is not a pilot lamp this time, but rather the coil of the F contactor that makes or breaks connection to primary voltage physically hardwired in series to the normally closed set of overload contacts. As of yet, inputs 3 and 4 are unused. This hardwired connection between the F contactor coil and the normally closed set of overload contacts may seem to be an injudicious use of a PLC with a stated ability of flexibility without the time-consuming necessity of rewiring. However, this is a common practice for reasons of safety. Similar to our earlier discussion about well-placed E-stops, note the physical connection between the F contactor coil and the normally closed set of overload contacts allows the overload to have the last say as to whether the F contactor closes or not, and never surrenders complete authority to the PLC. Wired in this fashion, the normally closed overload serves as a means of, again, overriding the program if it needs to do so. If the overload is cool and in the deactivated closed state, the PLC can energize or de-energize the F contactor coil as seen fit by the program. If, however, during the course of operation, the motor experiences a dangerously long period of sustained current draw due to a locked rotor, misaligned shaft, unusually high torque, or some other undesirable scenario, the overload element quickly opens and directly de-energizes the F contactor coil, all without relying on the program to do so. This is great, but one might recognize an issue with this technique. The obvious oversight being, how does the PLC know that the motor is overloaded? If the PLC controlled system continued to energize output Q1, and if the overload was in automatic reset mode, the moment the overload cooled, the motor would turn on again, and if the condition persisted, would overload again. A very simple solution to this scenario is the incorporation of the F1 auxiliary contact as an additional input to the PLC-controlled system. Recall that contactors, in addition to a coil and primary contacts, often include accessory pilot-level auxiliary contacts that change states when the coil is energized and the contact carrier is pulled in. This accessory input is essentially feedback to the PLC, verifying the F contactor has pulled in and the motor is in fact energized. If all goes well, the PLC should energize the output and very quickly receive confirmation that the F contactor has closed. If, however, during the course of operation, an overload occurs, the overload element directly de-energizes the F contactor coil, and both the primary and auxiliary F1 contacts return to their deactivated states without the involvement of the PLC. However, by virtue of the F1 auxiliary contact, the PLC is made aware that the F contactor is open because of an overload and can initiate any special actions specific to the process under its direction. Other feedback methods for motor starters exist. However, this, in my personal opinion, is the one that delivers the most bang for the buck. We'll explore PLC-controlled motor starters in much greater detail in later lectures. However, for the purposes of this lecture, you should realize that by physically hardwiring the F contactor coil in series with the overload, the motor is protected from overloads without relying on the PLC. However, by incorporating the F1 auxiliary contact as a feedback input element, the PLC is made aware of the overload. Note, this same system may be illustrated far more efficiently in the following fashion. Again, before moving on with the rest of the contents of this lecture, I recommend pausing it and comparing the two diagrams until you can understand the direct one-to-one correspondence between the confusing pictorial and the far more compact schematic representation. Moving on. Let's now address one of the earliest concerns I mentioned when introducing PLCs into the mix, that of PLCs and field input and output devices operating at different voltage levels. Pilot voltage comes in all flavors, notable examples being 120 volts AC and 24 volts DC. In a perfect world, one would just choose a desired pilot level voltage and then purchase switches and contactors and solenoid operated valves that operate at this level, then pick a PLC that operates at this same level, and then call it good. The problem is you don't always have this freedom because the system or PLC operates at different voltage levels than the commercially available devices, or vice versa. A simple solution to this voltage mismatch is through the use of interface or interposing relays. As implied by their title, interposing relays are devices that simply translate between one voltage level and another. To convert from 120 volts AC to 24 volts DC, one would purchase an interposing relay with a 120 volt AC rated coil with 24 volt DC rated contacts. Similarly, to convert from 24 volts DC to 120 volts AC, one would purchase an interposing relay with 24 volt DC rated coil and 120 volt AC rated contacts. Like normal relays, an interposing relay has a coil and electrically isolated, mechanically linked associated contacts. When the interposing relay coil is energized, the contacts change states. When the interposing relay coil is de-energized, the contacts return to their deactivated states. There's all sorts of creative ways to use interposing relays, but I think the simplest way to do so is as follows. Consider a scenario where we've got a PLC that operates at 24 volts DC. However, we need to use 3 field input devices. Let's assume they're a normally closed momentary contact red push button, a normally open momentary contact green push button, and the F1 contact or auxiliary contact that all operate at 120 volts AC. To interface the field input devices operating at 120 volts AC to the PLC operating at 24 volts DC, one would hardwire the 120 volt AC rated push buttons and auxiliary contacts such that these inputs do not directly energize the PLC, but rather selectively energize or de-energize the 120 volt AC rated coils of interposing relays IR1, IR2, and IR3. Then, one would hardwire the interposing relay IR1, IR2, and IR3's 24 volt DC rated contacts such that they make or break connection to the PLC 24 volt DC rated input. The task of interposing relays IR1, IR2, and IR3 is to translate the 120 volt AC input into 24 volt DC level pilot signals usable by the PLC. A similar methodology is used when interfacing field output devices with a PLC operating at different pilot level voltages. Let's assume the F contactor coil is 120 volt AC rated. To interface the 120 volt AC rated F contactor coil in series with a normally closed overload element with the PLC operating at 24 volts DC, one would hardwire the PLC Q1 output such that it selectively energizes or de-energizes the 24 volt DC rated coil of interposing relay IR4. Then, one would hardwire interposing relay IR4's 120 volt AC rated contacts such that it makes or breaks connection to the 120 volt AC rated F contactor coil hardwired in series with the normally closed overload contacts. The task of interposing relay IR4 is essentially the opposite of IR1, 2, and 3, being the translation of the 24 volt DC pilot level signals used by the PLC into 120 volt AC usable by the field output device. When the 24 volt DC Q1 output of the PLC is de-energized, interposing relay IR4's coil is de-energized and its associated 120 volt AC rated contact is in the deactivated open state. The F contactor coil would be de-energized and the motor would be stopped. When the 24 volt DC Q1 output of the PLC is energized, interposing relay IR4's coil would be energized and its associated 120 volt AC rated contact changes to the activated closed state. The F contactor coil would be energized and the motor would start. Used in this manner, the interposing relays are in effect acting as messengers between the field input-output devices and the PLC operating at different voltage levels. While a somewhat indirect and inelegant game of telephone is being played, using this methodology, it does allow for ordinarily incompatible devices to play nice together and accomplish some larger task. Adding interposing relays to a PLC only slightly complicates the schematic representation. Here the hardwired connection between the 120 volt AC rated e-stop and the field input devices does not directly energize the PLC input, but rather the 120 volt AC rated coils of interposing relays IR1, 2, and 3. The 24 volt DC rated contacts of interposing relays IR1, 2, and 3 in turn directly energize the PLC inputs I1, I2, and I3. As previously, the field signals kind of disappear down the PLC rabbit hole. With regard to the output, similarly, PLC output Q1 does not directly energize the field output device, but rather the coil of a 24 volt DC rated interposing relay IR4. The 120 volt AC rated contacts of interposing relay IR4 in turn directly energize the field output device, the F contactor coil, physically hardwired through the normally closed e-stop and the overload contacts. As previously, the hardwired connection of the normally closed overload relay directly de-energizes the F contactor coil in the event of an overload without resorting to the PLC initiated commands. When illustrated in this fashion, you've in fact got two schematics, a 120 volt AC rated schematic and a 24 volt DC rated schematic that interact with one another through the use of the interposing relay intermediaries. The top input portion of the 120 volt AC schematic delivers field inputs to the top input portion of the 24 volt DC schematic, and this in turn delivers the field input to the PLC. Interposing relays IR1, IR2, and IR3 act as the go-betweens for the 120-volt AC rated field input devices and the 24-volt DC PLC. In contrast, the PLC delivers output to the bottom output portion of the 24-volt DC schematic, and this in turn delivers output to the bottom output portion of the 120-volt AC schematic and field output devices. Interposing relay IR4 acts as the go-between for the 24-volt DC PLC output and the 120-volt AC rated field output device. Note as previously, the schematic implies the inputs are disappearing down the rabbit hole and gives no indication as to what conditions energize the output. This is meant to insinuate that a technician needn't worry their pretty little head about such details, since the PLC program is intended to assume this responsibility and only the devices be hooked in this fashion to do so. Yes, the use of interposing relays is somewhat tangled and necessitates a bit of organization on the part of the reader. However, it's often necessary to interface elements with one another in the following fashion if they operate at different levels of pilot voltage. Be aware that variations of this interface methodology exist that may or may not be more or less confusing to the reader. I find this method the least perplexing of the available more perplexing options. Before finishing this lecture, I recommend pausing it and comparing these diagrams until you understand the direct one-to-one correspondence between the confusing pictorial and the far more compact schematic representation. Assuming you can recognize this correspondence, this wraps up our brief discussion of PLC interface methods. We examine the placement of e-stops, overloads, and auxiliary contacts in PLC-controlled systems, and how these devices can be physically hardwired into a system such that safety is not compromised. Additionally, we examine how interposing relays can interface elements intended to operate at different pilot level voltages. Finally, we examine how a PLC control system can be efficiently represented using compact schematics. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.